Okay. Um, Today's session, we're just gonna cover. Sorry, I feel okay. Hopefully, like the audio is like not awful. Hello, how's it going?
Oh wait, no one.
No, I'm here. Sorry, can you hear me?
Okay, yeah, I hear you. Wait till
Okay,
show
are
up.
we good? I just want to make sure the audio is working.
Yeah.
Okay, cool. Sounds good. So today I was just gonna sort of cover some like implicit differentiation basics as well as like linear approximation stuff. Unless you sort of have something that you'd rather go over instead, which I can also sort of like do as well.
Well, let me just like look at the web assignment. Like the last one, like the one with Susan.
Yeah, because I just okay, because I just I've also hold on. I've also got some stuff just over like basic differentiation stuff, like the limit definition of it, as well as like the different like power, like the rules, like product power quotient rule, chain rule, things like that. I covered all of that in the session that I posted that didn't have audio, unfortunately. So
Okay.
I can do that, but I think it's all up to like sort of like what you
want. Okay, yeah, I'm just like pulling it up. Now.
Like, do you know any concepts specifically that you're sort of like having trouble with?
Okay, yeah. Yeah, let me just like share my. Yeah, like I feel like I was kind of. I just don't really understand like why it had to be you for like this one. I mean, this is like the first time I'm looking at like these answers, but yeah.
Okay. From y equals f of u equals g of x. So you said it was good time. Okay. So I can say that for the second one, I mean, we can like do that derivative together because that's just chain rule stuff, right?
Yeah, because like I understand like the formula for the chain rule or whatever, like. But.
Okay, sounds good. Yeah, the first part I think is just they're being a little weird about
Okay.
how it works. But I mean, at the same time, they say like, okay, if we say f of x, so the problem I'm just gonna like write it out. Yeah. What is it? It's y equals cotangent of cosecant of x, right?
Yeah.
Okay. So they want us to write it out as like f of u, and then u, right? Did I write that right? Yeah. Okay. So they want us to write it as. Sorry, no, I didn't. f of u and u. So you define u properly, right? So you said, okay, u is the inside function, right? U is cosecant of x, right? Which is right. But then you said that like your f of u was cotangent was a what's the word?
Yeah.
Oh, what?
Okay.
So.
Do you want me to keep sharing?
What'd you say?
Do you want me to keep sharing the screen?
No, it's okay. It's okay.
Okay.
So you said that your f of u was cotangent of u, right?
Yeah.
So normally I'd say that's how should I say it? So like normally when we're sort of like doing these things like because we're trying to like basically split them up into being like, okay, this one's like the bigger function, and this one's like the smaller function, or like the inside out function, and this one's the outside part. So you got the inside function part right, but when you sort of like do this, it's kind of I don't know. I think they just want you to sort of like, rather than say like, okay, it's going to be embedded within it, like, because this technically like suggests that that's embedded within this already, right?
Yeah, I was kind of like confused about that. Okay,
Or
yeah,
they're looking for just like it explicitly being separate.
yeah,
Does that make sense? That's kind of that question, I think, which is kind of weird. Okay. So I'm sorry about that, but sort of makes sense. I think they just want you to more explicitly like separate the two. Keep things in terms of x, whereas like that's sort of like that thing. Okay. As for like doing the actual derivative, if you want to, you can sort of like do that real quickly, I guess. Do you know what the derivatives of cotangent x and cosecant x is? What they are, I guess.
I mean, not off like the top of my head. I've kind of just been like looking them up.
No, it's pretty good.
In the book.
No, honestly, like you don't even need to know. Like I don't know these off the top of my head right now. You don't really need to know them.
But it is like nice. It is like nice to know them though. Okay, I'm just looking them up.
Okay.
Okay, yeah. Cotangent of x is negative cosecant squared x.
Yeah.
And then cosecant x is negative cosecant x times cotangent x.
Yeah, exactly. That's what I've written out here. So when you want to sort of do this whole derivative of one within the other, the best way to sort of like learn how to sort of do this is by literally just like writing it out very explicitly. Like, okay, I'm doing like this derivative, and then keeping I'm doing the outside derivative, or I'm doing the derivative of the outside function and keeping the inside the same, and then I'm multiplying by the derivative of the inside, right? That's what makes sense. Okay, cool. So, how should I sort of like write that, do you think?
Okay, so f of u is cotangent, so then it would just be like negative cosecant squared cosecant x, like in parentheses, and then times negative cosecant x cotangent x.
Yeah, exactly.
Okay. So then what do I write?
And then that simplifies, so I can just, well, actually it doesn't.
Okay.
Right? I don't know if you can like.
Yeah. Okay. Yeah. So yeah, on WebAssign they just have it like, it's just like cotangent x times cosecant x times cosecant squared times cosecant x. Okay. Yeah. I like.
Yeah.
I'm pretty sure out my attempts for this one. So I think it's like the way I wrote it or something.
Yeah, because those negatives get rid of each other, right?
Yeah.
Cool. Okay. So yeah, I mean that's a pretty good example, I think, of like sort of how chain rule works. Is just like, okay, you keep that inside the same, do the derivative of the outside function, or you plug this into like get like x, for example, if you're only looking at the outside. And then just take the inside and then multiply by the derivative of that.
Mm-hmm.
Cool. Cool. Do you have any other? So are you good with this example?
Yeah.
Cool. Do you
Yeah,
have
also
anything
good.
else that you sort of like encountered?
There was like another question that I got wrong on that website, but it has like it has like an attached solution where they like go through the steps. So yeah, I probably just like, I mean, yeah, I guess we could like, hold on, let me just, okay. Okay, so take care of that.
So do you see how they got to that first step?
Yeah, so there's
F of theta.
Yeah.
That squared goes to the front of the secant because the.
Wait, so why would they put it in front of the secant again?
What do you mean?
Why do they write it like 2 secant of like 4 theta times?
So you'll see that like your outside function in that case is u squared, right? So they do the derivative of u squared with respect to u, so they make that like the 2 go down, right? So then the derivative of u squared with respect to u is 2u, right? And then they just basically plug u in back in for secant of 4 theta.
Okay.
And then they multiply by the derivative of secant 4 theta, which is
okay. So like f of u is u squared, I guess, and u is like secant of.
Yeah. So your f of u, so yeah. So you have your what is it, f of theta?
Yeah.
Equals is it? It's secant squared of 4 theta, right? And so they wanted you to be like, okay, we have like our f of u is u squared. Or I guess x squared. Honestly, I'm not really, this is weird. So I'm just gonna say u squared because honestly, like that kind of makes more sense in a way. So I'm just gonna do that. And then your u in this case is your secant of 4 theta, right?
Yeah.
And then, I mean, all you sort of do then is just focus on just this. So then you know that you have to do like, okay, so like the derivative of, or I guess d by d theta, my bad. Of f theta would be this f of u, right? And then times just like u prime, right?
Yeah.
So like you take your u, you do the derivative of this, plug u back in, and then multiply by that as well.
Okay. All right. Wait, let me just. Yeah. I mean, yeah. I could probably just like go through it like.
The best thing that I can just I mean I think you're getting it. I feel I just think at this point like just practice with the problems and sort of like looking at how to sort of just like go through all of the different things is the best thing that you can do for yourself. I know that like going through problems is really annoying and tedious and awful, but like calculus is a muscle, pretty much. Like you have to sort of like work on it over time. And I guarantee that like the more you do these things, the more like instant you'll sort of recognize like, oh, clearly I can like see, okay, like the square's on the outside, so I just have to bring 2 over, and then I multiply by literally the inside, and then that's like it. You know,
Mm-hmm.
it's pretty quick. But then you also have to notice that like this is itself is also something. There's something in here, right?
Mm-hmm.
So then you also have to think of like, okay, f of say v is so the outside function here is your secant v, and then with v being equal to 4 theta.
Oh, okay, yeah, because it's like a.
And then it kind of goes back in, and then it kind of goes back in again.
Mm-hmm.
A lot of stuff. And so that's why later on, yeah, you do this, but then you need to do another round of chain rule.
Mm-hmm.
And it keeps repeating until you don't have an outside inside function, right?
Mm-hmm.
There's nothing else to like sort of put in there. Right?
Yeah.
So hopefully that makes sense.
Yeah, probably like.
Everything's sort of like very separate too, because like when you find this u of prime, like this stuff goes in here. So this is your like prime v, like times v prime. And like this basically goes away, and then you have to think about like this.
Mm-hmm.
So they're like separate derivatives.
Yeah.
Cool.
Yeah, I think that's like all the questions I have for that WebAssign.
Okay, that's good. Are you sort of like, I'm assuming you sort of like understand like power product quotient rules, and it's just maybe this chain rule that's sort of like tripping you up.
Yeah, I took like I started off last semester taking calc, but then my professor said that like I would probably do better in long calc, so I just like took it last semester because like I took like pre-calc senior year, so which is basically it's not like it's very much like algebra 2, so like
Yeah. Okay, I understand. Yeah, I mean all these concepts and stuff are really hard, and I know that like this is sort of where long calc stop, right?
Yeah. So hopefully I can like actually keep.
Are you like, how's like implicit differentiation with you? Or are you sort of like?
Yeah, I mean like. I don't know. I mean, I kind of just like go to lecture and like copy the stuff. Like I feel like I don't really like. I don't know.
Yeah. I know what you mean. With respect to like, I know. I feel like, I mean, it's so early in the morning. It's hard to like ask me questions.
Yeah.
So, you know. I know. I'm there every morning in person. It's very few people and like quiet and kind of stuff.
Yeah. Yeah. I like hadn't gone this past week because I like got contact trace, but yeah. It's just...
I understand. Yeah. I think like. Sort of like I mean, I can't just say like you just have to like follow his words and like understand like the path he started taking with all the things, but like that's kind of the thing is like that, or like reading through the textbook and trying to like look at examples and be like, okay, like maybe think about why he's doing certain things. Because I mean, I've been paying attention to like his lectures and stuff. I mean, he does a pretty good job of just sort of like laying out like sort of everything pretty well. It's just like if you miss it, then it's like you're not gonna like say it over and over again, you know.
Yeah.
But
wait,
so
like for the textbook section, because I feel like is he like going on the schedule like that's on Canvas?
Yeah, I'm not sure honestly. I feel like I feel like we might be, because his lectures are not like where you're doing section this and then section this like each day. He sort of like overlaps around.
Yeah.
And he's on pace, but it's not like very explicit. Like I learned math pretty much like every single time I've taken a math course in college. Like where it's like, okay, I pull up to lecture and then we cover like a section, like a specific section in the textbook. And then over like a few weeks, we'll get through a chapter, things like that. Earlier in the class that I'm currently in right now, it was not like that. It was very much like how Bradshaw's doing it, where it's sort of just like learning, but not like very specific, and it's hard to sort of like figure out where in the textbook you're learning from that. And so I understand what you're sort of like talking about. So just try to like recognize, okay, this is like the main topic of this lecture, or like something like that, or think about, okay, if I'm trying to read in preparation for the next lecture, what did we just do? Look in like the little schedule thing. He's probably gonna like follow the schedule, even if it's like sort of bleeds into one lecture or another, right?
Okay. All right. Yeah.
That makes sense. Yeah, but I know what you mean, and like, yeah, I think the textbook, it's like, I hated learning from textbooks, and then last semester I was in the Hyatt for like a total of like 28 days, and that adds up to like over 10 like calc lectures that I missed. And so I had to do a lot of like learning from the textbook. And it's best to just sort of, you don't need to understand literally every single thing that they say, because some of the examples that they're going to go into are just like irrelevant and don't matter. But when they're like going, like introducing concepts for the first time, then if you try to like read the beginning concepts and then don't fully understand it and then keep going, it's going to be really, really hard to get through the rest of that text, because you're not going to know what's going on. Like the rest of that section, you're not really going to know what's going on, right? So try to like look at those earlier examples, you know, like watch some videos online, and then once you sort of like get the general idea, like more of the harder examples that they do aren't really that necessary, honestly. I just think that's probably something to like think about. Okay, well, she just left. I'm hoping it was because she probably computer died or something. Um, if it was, I'm just going to sort of like set up a problem and start talking about this part of implicit differentiation, just because I want to sort of make sure we're all good on that. I know I covered a bit of implicit differentiation last time, but it was a lot of like one example. So I'm just going to cover another example that sort of shows it in a bit of a better light, I think, if that makes sense. So basically the idea here is that we want to find, without just using the formula, the derivative for the inverse sine of x. So I'm just going to write up f of x equals, well, I like using arcsine. Just makes me, I don't know, it kind of sounds cooler. So find x. Okay. So we want to use implicit differentiation, right? I mean, that's what the whole example is. Honestly, like the reason why I'm using this as an example, not as an exam question, because I don't think I'd be able to like, I mean, it's basically like a mini proof of how we know what the inverse, what the derivative of invert like arcsine is. Not really like a proof, but it's just sort of like showing you how it's like we've sort of gotten there. But I'm just going to take you through the steps sort of how it works. So we sort of start out by, instead of writing it as like f of x, it might be a bit easier for us to write it as like some output y for our input, our sin s x. And then I can notice that, okay, y is our function, x is our like variable, right? Or I guess y is a variable, but it's also like, it's more about the output. So, but what if I like sort of like switch this and found basically like the inverse of this function, pretty much. And so you do sine to both sides, you get sine of y equals x. Okay. So this is something that we do know how to take the derivative of, right? Because we know that derivative of sine x is cosine x. Awesome. So maybe we can do something with this. But I mean, yeah, our variables are switched around, but I mean, that's kind of the idea of implicit differentiation, right? Is sort of being able to like deal with that. So let's try to, what should I say? How do I want to go with this? Okay, let's write this out just sort of like using the rules of implicit differentiation, which basically means, okay, I'm going to take this y variable, which again, I basically corresponded to some function x, f of x, and I'm basically implying that y is a function, and therefore when I take the derivative of sine of y, I need to imply chain rule. And then do basically the multiply, I take like the normal derivative of this, but then also like multiply by the derivative of just y. Because y is again like a function that we're sort of implying exists. So if I did the derivative of both sides, I'll write that out. Yeah, I did the derivative of with respect to x of both sides. And the reason why we have to like imply that it's a function of x is because, I mean, again, like that's literally what we did up here, right? And if we were doing the differentiation with respect to y, then we wouldn't actually have to, do the whole like implicit, do the whole implicit differentiation thing. But again, like we assume y is some function x. So we do this, then we get cosine x, cosine y, because the derivative of sine is cosine, right? But again, multiply by that, and apply that chain rule, multiply by the derivative of y again. It's basically like sort of the core part of implicit differentiation. And this is just one, right? Awesome. Okay. So you'll notice that this part right here is actually exactly what we're looking for. We're trying to find the derivative of y, which we've assigned to be arc sine x. And that's exactly what this means, right? Because we're trying to find dy with respect to x of arc sine x arc sine equals, no, I'm not sure, right? So all we have to do now is just solve for dy by dx, right? So this is going to be y 1 over cosine y, because I have to divide cosine y by both sides, right? Okay. But now, like, the big question that I have to sort of answer for is, what is cosine of y in the first place? If we find out cosine of y, then, I mean, we know what the derivative is, right? Okay. We know the derivative of arc sine x, right? Because that's what this means. Cool. So we have to be a little creative here. I'm just going to give the answer. I mean, we have sine of y equals something, right? So maybe using the sine of y, cosine and sine are pretty related. Maybe we can find a good way to sort of define what the cosine of y is, right? So I know that like sine and cosine are sort of having to do with like the ratios of right triangles. So maybe I can write out a right triangle, draw a right triangle to sort of model what's sort of like happening here, right? So sine of y equals x. SOHCAHTOA and outside of hypotenuse is for sine. So that means that because x is just x, that means the outside of the triangle could be x, and then the hypotenuse could be 1, because then it'll just be x over 1, which is x, right? We call this triangle. What is it? So this is x, this is 1. And then this side A, we'll say is A, is the side we're trying to solve for, right? Okay. So we can't really just say like, oh, okay, easy, like so okay, A over hypotenuse, so cosine of y is therefore, cosine of y is therefore A. Like we can't really do that very easily just because we don't know what A is. So we need to find out some way to sort of write A in terms of x. Yeah, this is a right triangle. Now the thing about a right triangle is that we actually have an equation for the different sides, right? Which is the Pythagorean theorem, right? So if you sum both, I mean, you know what it is. A squared plus b squared equals c squared, right? Okay, so if we do a squared plus x squared, because that's this side's length, plus 1 squared, or just equals 1 squared, sorry. You can just simplify to 1. We can put this into a squared equals 1 minus x squared. Then solve for a, we just take the square root, right? Cool. So now we have a in terms of x, which we know works out because, I mean, x is sort of like a part. It's like one of the variables that we're trying to working with. So we can write that. 1 minus x squared. Awesome. Root of 1 minus x squared. So because we have that written as in terms of x, now we can find the sine of this and say that it's, I mean, the cosine of this triangle and say that it's the cosine of y because I mean, I guess I didn't write this out earlier, but this angle right here, that's your y because when you plug in like any kind of input for a trigonometric function, such as what we've done here with sine of y, then that input corresponds to an angle of some kind of triangle, right? So now that we have this angle y, we can say that, okay, now we can find the cosine of y, right? Which all we need again is just the adjacent side over the hypotenuse. So cosine of y equals a over 1, right? But we've found a in terms of x. So we can just say that it's square root of 1 minus x squared over 1. Cool. And now that we have cosine of y in terms of x, because that's what we're looking for down here, we can just plug that into here. And because this is sort of upside down, I mean, you can pretty much just get rid of this, right? This is just sort of like by itself. This is in the denominator of this fraction. Then we can just say that derivative of y is 1 over 1 minus x squared. Basically, just by plugging stuff in. So that's how we sort of found. And then again, like that's f prime of x. So yeah. So like this key step, this part right here is like the key step to all like the implicit differentiation, right? So again, you do the derivative of your function of, I mean, I guess it's a function of y, because y is sort of like inside the sine, right? So you do the derivative of that with respect to x, do it normally, and then you multiply by the derivative of just y again. That's really important. Again, you're basically implying chain rule. I went over this pretty in depth. I did a pretty in-depth look as to why we do this in the last session. I strongly recommend you check that out if this is sort of confusing you. I promise that will show you how it all works. You check it out. I'm not going to do it again right now. Okay, cool. So yeah, that's just like one example. Awesome. I am now going to go over some linear approximation stuff. Linear approximation is cool because, I mean, it's kind of in the name. It basically takes some, let me find it in my notebook, just so I don't write anything wrong down. It basically takes some like Curry function that is sort of like hard to, might be hard for, calculators to find, and then basically zooms in a lot, and then eventually that curve looks pretty much like a line, right? So we have like this, we're sort of like going all over. Sort of looks the best way to do it. We get this line right here. And like if you zoom in really, 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 really close, these are gonna look very similar, right? I guess I can draw this a little bit better. So if I draw like this line, kind of like that, where these touch, then there's going to be a difference right here and here, right? So that's kind of the idea of linear approximation is like, okay, let's find the tangent line at some point for x, and then use that, which would be right here, right? And then use that to approximate, well, I guess this is a. And then use that to approximate the real value that we're trying to find. So it's basically like, okay, we have an input, but it's harder to find like the real value of it. So make it an easier problem, which again I'll show an explanation of this later. Make it an easier problem. Just do a straight line, like a linear line, using some slope that we find, which again I'll show you. And then plug, and because it's linear, we know that we can basically just like plug pretty much any value into that linear, into the equation of that line, and then it'll like, we'll be able to solve it pretty much okay. Sorry, that was a bad explanation. Okay. So the first example I sort of want to like go over is using it to evaluate something such as 8.1. The cube root of 8.1. So normally this is like pretty hard to find. I mean, I don't know what it is off the top of my head. It's like a decimal, and like cube rooting is like a whole like very complex thing. But something that we know we can find is the cube root of 8, right? Which is just 2, because 2 to the third is 8, right? So we have this function f of x was cube root of x. Then we know that if we just plug in, okay, 8.1 in, we'll get cube root of 8.1, right? Or if we plug in 8 in, we get cube root of 8, which is 2. We know that. So to sort of correlate this idea to here, this black stuff is basically, this black equation is basically like the real line that we're focusing on, that we want, like, that has a true value on it, right here. So like, this is sort of our fake value, right here, like y prime, I guess. Or yeah, y2. How about we say y2? Whereas this is our real value, y1. And since we're only an approximation of y1, y2 is fine. So we're going to use this idea, the tangent line of this idea, to find an approximation for this 8.1. Okay. So you might be wondering, okay, like how does this make any sense? Like how do we do that? Well, one way we can start is if you think about this x as being our 8.1. This a is our 8. Then we can think, okay, don't we need the that's a place where we can find a tangent line, right? Because this black line is f of x. So all we need is to just find the tangent line at 8, at x equals 8 of f of x. And then we can plug in 8.1 into that tangent line, and then we'll get, our value, right? Okay. So how do we find that tangent line? Well, we need the derivative, right? To first calculate the slope of it. We need the derivative of that original function. So if you can sort of write this out in a different way, it's the 1/3. An derivative, it's a simple power rule, so you get 1/3 of, it's just 1/3 and then times x to the 1/3 minus 1 is -2/3. Make sure I'm good. Yep, I'm good. Awesome. And now what we need to do to find the slope of the tangent line at this point 8 is plug it in, right? Is plug it in for x in this derivative function that we have. So we just do f prime of 8, 1/3 times 8 to the -2/3. So 8 to the -2/3, I guess I can just like write it out a little bit differently. It's basically just like 1/3 times 1, because the negative, so you can put it on the bottom. The 2 corresponds to like squaring this quantity, and then your over 3 represents like the cube root of the quantity. So I'm going to write it as the cube root of 8 squared on the bottom because of the negative, right? So 1/3 times cube root of 8 is 2. 2 squared is 4, so it's 1/4. There's 1/12, okay? So this 1/12 represents our slope. It was n, our slope of the tangent line, right? Okay, cool. So we're almost there because, as you should know, the parts that we need to write any kind of line equation for, any kind of line equation is either a point and the slope or 2 points, and then we can find the slope between those and then just plug it into one of our multiple formulas, right? Which include a slope-intercept form or point-slope form, which is pretty much like the easiest thing that we can do here, right? And point-slope form is actually pretty much the reason why we're sort of doing this whole, okay, choose 8 instead, right? Because normally when you do point-slope form, you need to know the output of some input, right? You need to know a point. So if we sort of take the cube root function and plug in 8, we know we're going to get 2. And so that point, 8, 2, is our point that we're going to use for the slope, point-slope form alongside the slope, right? So if we want to write like equation of tangent line, point-slope form has the form y minus y1, or y1 is like an actual value, whereas y is just like the variable, equals m x minus x1. Or you could write it as y minus like f of a, where f is a function that we're using, so that's like the output, and then m x minus a, where a is the value, the constant that we're plugging in to f of x. Okay, so if we're going to use this idea for this line, because yeah, this is the line that we're trying to find. So we're trying to find the tangent line at this specific point on f of x. Okay, we're going to use x as our input, so that would be, make that a. So we need x minus 8, right? And then m, we just about m, it's 1/12. And here it's y minus our output of the function, which is 2. So again, plug in 8 here. 8.1 is, y2 here. Okay, wait. Shoot, I like did this wrong. Okay, so this is the value that we're trying to get is y1. Y2 is, hold on. Okay, wait, I did this wrong, sorry. So y1 is what we're trying to get out of this, right? And then we know that this is going to be different from our estimation right here. So y2 is 2, because we're still like plugging it in along this line, right? That's the f of x line. And this isn't actually what cube root of x looks like. Well, I mean, it might be, I just forget. Actually, yeah, so, but don't worry about that. I'm just trying to like use it as an example. So 8, 2, okay, so we know that 2 is sort of our output here, right? So we have our point slope form. Now we can just solve for y. So y equals 1/12 x minus 8/12, which is just, what, 3/4 plus 2. Right. Or I guess we could, actually, no, that's a bad way to put it. Let's just keep it as y equals 2 plus 1/12 x minus 8. Okay. And so this is the tangent line of f of x, which is our x, the cube root of x, at the point x, yeah, at the point 8, 2, where x equals 8. All right. And so this also sort of represents that whole linear approximation thing that we've sort of were introduced to in lecture, where like that's basically the formula that we can plug in for some x, right? Which is what we're going to be using right here. So you plug that in for x in this equation, and then our output of that will be the final sort of like thing that we're trying to find, which is this, or an approximation of the thing we're trying to find, right? And so this just represents, if you're trying to like put it onto big terms, coming from here, we found f of a, right? So 2 is f of a, because we're using, again, f of x. This is a, this is f of a, because it's the output, okay. Plus f prime of a, right? Because we found the derivative, plugged in a right here, and found the slope. F prime of a is the output of this input for the derivative. And then x minus a again, right? So it's all dependent on what we choose up here. So, and whenever you see a problem like this, they'll probably give you a value to use as a. It'll be like, okay, use a equals something to estimate this value, right? And it's all about just like defining, okay, like what's the equation, what's the function of like the hard to compute thing, and then how can I like plug a into that all these different times, then find your inevitable approximation, right? So if we eventually plug in 8.1 for x here at the end, do L 8.1 equals 2 plus 1/12. So 8.1 minus 8. That's just 0.1, right? Or 1/10. Simplify a little bit. 2 plus 1/20, which comes out to be about like 2.0833333. Repeating. The actual value of root 3 8.1 is what? 2.008 2.08299 repeating or something? Oh, not repeating. Okay. So it's about that. Oh, wait, fix that. So, as you can see, like this is a pretty close approximation of sort of the value that you're trying to get. Although in our case, again, this graph that I showed up here is not what we're doing. It's just sort of an example of how we sort of like figure everything out. So there's a reason. So there's a reason why this is higher than this, even though like, what we found is that it's going to be lower, and it's sort of dependent on whether or not the function at that point is concave or convex. But I don't think we've gotten there yet. So you'll figure that out in the meantime later. So hopefully this example sort of makes sense. I can go over it again when people are actually here, because I don't think I'm very good at teaching yet when people are not actually here, like asking questions for me to like sort of be engaged with them. So yeah, okay. I'm gonna end the session here because no one's showing up and I went over this example.